Can a quantum computer steal your Bitcoin? Right now, the honest answer is no. But there is a real long-term threat, and it's not the one the headlines are selling you. Let's separate the hype from the reality. Bitcoin leans on two pieces of math. ECDSA signs your transactions and proves you own your coins. SHA-256 powers mining and hashing. Quantum computing threatens these two in very different ways. The real danger is Shor's algorithm. A large enough quantum computer running Shor's could take a visible public key and work backwards to your private key, then quietly spend your coins. That's the part worth understanding. But here's the catch that changes everything. Shor's attack only works if your public key is already exposed on the blockchain. No exposed public key means there is nothing for the algorithm to reverse. What about SHA-256? That's where Grover's algorithm comes in, but it only gives a quadratic speedup. It roughly halves the security, from 256-bit to about 128-bit. Mining stays hard, difficulty adjusts. This is not an extinction event. So the whole risk hinges on one question. When is your public key actually exposed? The answer depends entirely on the type of address you use. Picture an exposure ladder. Old pay-to-public key coins from the Satoshi era show the key forever, highest risk. Reused addresses reveal the key the first time you spend, high risk. A fresh address shows only a hash, low. So the lesson is clear. Old coins and reused addresses are the real targets. A fresh, never-spent address only exposes a hash on-chain. Your public key stays hidden until the moment you spend. This leads to a sneaky strategy called harvest now, decrypt later. An attacker records your exposed key today, waits 5 to 10 years for the hardware, then derives your private key retroactively. Old exposed keys stay vulnerable. Now the reality check, the hardware. Headlines love to shout qubit counts. But there is a massive difference between the qubits they announce and the qubits an attack actually needs. Physical qubits are noisy, raw material. Logical qubits are error-corrected, and each one is built from many physical qubits. 1,000 physical qubits is like 1,000 pounds of steel. It is not yet a car. Look at today's machines. IBM's Condor hit 1,121 physical qubits in late 2023. Google's Willow used just 105 physical qubits in an error correction demo. Physical, not logical. Now compare that to what breaking Bitcoin actually requires. One estimate models roughly 13 million physical qubits for a slow attack on an exposed key, and 317 million for a fast 10-minute race. Sit with that gap, around 1,000 qubits today versus 13 to 300 million needed. That is 10,000 to 300,000 times more than anything that exists. We are not close. So here's a realistic timeline. Through 2030, it's a monitoring phase. No public machine threatens ECDSA. From 2030 to 2035, developers seriously debate migration. Beyond that, it's conditional on the hardware. The defense already exists. In August 2024, NIST finalized its first post-quantum standards. For signatures, the new scheme is called ML-DSA. Math designed to resist even a quantum attacker. But there's a trade-off. A post-quantum signature is about 2,400 bytes versus roughly 70 for ECDSA, 30 to 40 times bigger. Bigger signatures mean fuller blocks and higher fees. It's like upgrading from a postcard to a small package. And Bitcoin can't just flip a switch. It needs consensus. A fork agreed on by developers, miners, exchanges, and wallet makers, plus a safe way to migrate billions of dollars in old coins. That coordination is the truly hard part. Here's what you can actually do today for free. Stop reusing addresses. Use a modern wallet that generates a fresh one each time. Keep your keys offline. Follow NIST and Bitcoin governance. And don't panic consolidate your old coins. Bottom line, no quantum computer can steal Bitcoin in 2026. The threat is real, but it's conditional and years away. Ordinary phishing and key theft are the live danger right now, so prioritize accordingly. For the full breakdown, head to itokenly.com.